Hello everybody and welcome back to our next hands-on in this artificial intelligence course. In this hands-on I would like to show you how we can do support vector classification using scikit-learn. Let's start as always. Let's import some libraries we need. So matplotlib inline to generate some plots, import pylab as pl, import numpy as mp. From sklearn.model selection import, and now I import several packages which we might use in this exercise. So cross validate, grid search, CV, and stratified k-fold. Then we import from sklearn the metrics package, and we import from sklearn the SVM, so the support vector classification. So that have been a lot of imports. Now let's execute this to see if everything looks fine. That's fine. And now we generate some toy data for this tutorial. So mp random seed 0. So let's set a seed that we all work with the same data, and then let's generate some x data. So x is equal to mp random rand 200,2. So 2 features, 200 samples, and now let's generate some a y variable for classification. And therefore I use the logical XOR of all the samples and feature 1 that are greater than 0, and x feature, the next feature greater 0. So let's plot the data to see what we have generated. Our figure is pl.figure, fig size is equal to 10,5. Then let's generate a subplot axis.figure at subplot 111. So 1 column, 1 row, first figure, and now we create a scatter plot axis.scatter. So x where y is equals to 0, feature 0, x where y is equals to 0, comma, this second feature. So at index 1 we give it a marker which is x. We say the color is black, it has an alpha value of 0.7, and we give it a label. Let's call this is class 0. Then we copy this line and we do the same for class 1. So y has to be then 1. The marker, we take the O, the color we change in green, and we give it a different label, the class 1. Then let's add some information. X set x label x1, x set y label x2. So we plot feature x1 against feature x2. We set some limits, set ylim to be -3 to 3, and we set the limits for the x-axis from -3 to 3. And then we have a legend, pl.legend, and we make a tight layout that doesn't have too many, that the margin is quite small. So let's execute this. And now we can see the data. So what have we generated here? We have generated a data set that has 2 features, x1 and x2. And the labels of this data set represent the XOR problem. And you see here that we have here some data points that belong to class 0, also in this space here, and there this labels belong to class 1, and this labels belongs to class 1. So now let's try to fit a support vector classification model that we try to separate this data. And therefore we use cross-validation. And I will show you now in this hands-on how we can do cross-validations using two different approaches that lead to the same result. So first, we said we learned that in the support vector regression, in the support vector classification, we have this parameter C, which is the trade-off between maximizing the margin and minimizing the training errors. So we have to find the correct C value. So therefore, let's generate an array of different C values which we like to try out. So in log space, mp.log space from -4 to 4, 10 values. And this we store in a dictionary. Params, our parameters is equals to C colon CS. So a dictionary, I will show you, has always a key value and values to this key. So if I like to access, for example, the key with the name C, I have to write here params, and in brackets I have to provide the key. In our case it's C, and this will then return the array which we generated here. So we could also extend the dictionary by providing here a different key. For example, test is equals to 9, and then you see that the params array has now two keys, one key that's called C and one key that's called test. So if I write here params.test, I can access the value with the key test, and then it returns 9. So let's remove this here and execute this line again, that we only have stored the C values for the key C. So we have now 10 different C values that we would like to try out in our cross-validation procedure. So let's define a cross-validation object. So our cross-validation is stratified k-fold cross-validation, and we say we would like to have 5 splits. So 5 fold stratified cross-validation, and we would like to store the best accuracy on our test data. So we create an empty list. So then we have learned also in one of our latest lectures that we can now use this stratified k-fold object to iterate through it. So for train index, test index in kf.split x, y, and now we can generate training and testing datasets. So x train is x train index. So train index contains all the indices of the training data. Then we write k x test is equals to x test index, and then we have to also do the same for our labels y. So y train is y train index, and y test is y test index. And now we have splitted the data into training and testing, and this we do for 5 different folds then, and now we can fit the model. So our model is a support vector classification. We would like to use in this example a linear kernel. Kernel is equals to linear. And then we like to perform an internal grid search to find the optimal parameter C. So this we can do with grid search. So grid search is equals to grid search CV. And this method from scikit-learn, grid search CV, takes as the first argument the model which we like to evaluate. So we provide here the model. Then it would like to have an argument with the parameters it should try out. So we, in this case, use this parameter dictionary here. Then we say the internal cross-validation should be 2. For example, we only like to generate 2 folds for finding the optimal parameters. The scoring should be accuracy, and our features are independent and identically distributed. This we set to true, because otherwise scikit-learn would throw a warning that this will change in the next version and so on. And this we can prevent by providing here this parameter. Then we use the grid search object to fit the model on the training data. So what is this doing now? This fit now executes an internal cross-validation using the model which we specified here. And internally, within this method, it tries out all the different c-values that are stored in this params array in a twofold cross-validation. And then internally, it already selects the model that worked best with the c-value, that worked best, and then it refits the model in the end after the training. So we can do here the training, and then we can already in the same step test how well our model works on the test data. So now we can do predictions with the best model. So our y-pred, our predictions is grid search dot predict. So we do now predictions with the grid search object because, as I said, internally after fitting the data, it already selected the model that worked best with the optimal parameter c. So we can do here predictions on the test data, and we can add best accuracy test. We append here metrics dot accuracy score for y test and our predictions y-pred. And we also can print here the optimal c value, optimal c equals to str grid search dot cv result best c. So let's try this out. If we get an error or not. So it tells me there is no attribute that's called cv result. So let's check this grid search dot. It's called best params. If I replace this here, grid search best params, and then I say it should return the best parameter c. And then in the end we transform this Python list into a NumPy list, np.array best accuracy, and then we print the best accuracy on the test set. The average accuracy on the test set is equals to %.2f and plus minus %.2f. And now we can pass here a tuple with the mean accuracy on the test data and the standard deviation. So let's execute this. This will run now for a few seconds, and now you see, okay, we get now here 5 different c-values because we did a 5-fold cross-validation, and the average accuracy on our test data is 64% plus minus 8%. So this indicates that our model does not work very well. So why could this be the reason? Why does our model with a linear kernel does not work very well? And that's quite obvious if you look at the data here. So actually with a linear kernel, we will never be able to find a line that separates these two classes optimally. We can try to find a line in this two-dimensional space, but it's not possible. We will never be able to separate these two lines. So what could we do? We could use a different kernel. But before we do this, I show you how we can write this cross-validation procedure even more efficiently using some of the other methods that are provided by sklearn. So I usually show you this because this makes clear how a cross-validation works internally. So we can also then do some additional things that are not possible to do with the standard methods that are provided by sklearn. So when we write our cross-validation procedure here, we also can compute here different other metrics and do some other interesting stuff within the cross-validation procedure. But we could also write this more efficiently. For example, we could write here our model is S support vector classification, and the kernel should be linear. So we try to reproduce the exact same results. Then I copy this line here. So we would like to do a grid search on the model, which I defined here, on the parameters, which we defined above. I like to do a two-fold cross-validation. I like to do a scoring with accuracy, and IID is true. And then we need an outer cross-validation. So the stuff which I wrote here, we also can more or less hide within one of the sklearn methods. So our outer cross-validation is now stratified k-fold cross-validation, and we would like to do 5 splits or 5-fold cross-validation. And now we can write in the next line, our cross-validation result is cross-validate. That's a function which we imported before from the sklearn package. You can see it here, sklearn model selection import cross-validate. And this method allows us to provide a model which we like to do our cross-validation on, and a cross-validation loop. So here we say, I provide here now the grid search. So the grid search is handled as a model. So it's passed as a model, it's doing internally then the cross-validation. And then I provide here CV, my cross-validation is now this outer cross-validation loop. I provide my data X. I provide my labels Y. I provide a scoring, which should be the accuracy score. And then I print at the end the results. So print average accuracy on the test data is equals to %.2f plus minus %.2f. And now I use this CV result and I use the test score. So that's a dictionary now. The test score dot mean and the CV result test score dot std, standard deviation. Now let's execute this. And I get an error because here is an S too much. So let's execute it again. And now you see that the average accuracy on the test data is 0.64, so 64% plus minus 8. So here I just needed 5 lines to do exactly the same stuff which we did above here. However, doing it this way gives you more flexibility, because then you can compute here in this internal loop also other metrics like the Matthews correlation coefficient or the precision and the recall, and maybe you can also generate within each of these iterations, you can generate different plots that visualize some of your data, which wouldn't be so easily possible with these methods that are provided by sklearn. However, doing it this way saves you a lot of work in writing code and is doing more or less exactly the same, which we did above here. So, as I said before, this is still not a very perfect performance, so we could try out different kernels. So let's copy the code here and paste it in here. And now let's provide a different kernel, let's say the RBF kernel. So now we know that the RBF kernel has also some additional parameters. We not only have to find the optimal C value, but we also have to find the gamma value, which is in front of the squared norm. So I copy the parameter dict here and paste it here. And now I extend here the parameter dictionary with an additional key, which I call gamma. And gamma should be also log space from -4 to 4, 10 values. So what we do now internally is we try out 10 different values for C, we try out 10 different values for gamma, and we try out every combinations of C with every combination of the gamma. So 100 different parameter sets are then fitted internally within this cross-validation procedure. So let's execute this. This might take a few seconds. And then you see that we now achieved an average accuracy on the test set of 97% plus minus 0.02%. So you can see using here a different kernel allows us then to fit a hyperplane that separates the data into a higher dimensional space. So this problem now can be solved, and we can almost make perfect predictions using an RBF kernel by implicitly more or less transforming the data into a higher dimensional space. So you see the kernels matters, and you can try this now out in the exercise, and you will also see that not always the RBF kernel is the best kernel. So it highly depends on your problem. Is your problem linearly separable, or is your problem not separable in a two-dimensional space? Then we need maybe different kernels. So there we also have to do some, or we have to collect some experience, we have to visualize the data, we have to get a feeling of the data, that we can then do the correct predictions, and that we can learn models that generalize very well. That brings me to the end of this lecture. Thanks, and see you at the next one.